Okay, so just as Mary suggested, I'm not really good at standing back there because that's not what I do. But I want to first thank my co-authors that I have here. Kristen Chestnut, a previous graduate student of mine, now is gainfully employed. Thank goodness, right? And then I also want to thank Dustin Smith and Dave Wellman from West Virginia Division of Natural Resources for all of their assistance in this project. Made a big transition from West Virginia to Missouri during all of this, and these guys were still nice enough to let me continue to work on the project. So when we talk about the Monongahela River, or the Mon, as it's colloquially known, acid mine drainage was a very problematic environmental concern there, and during this time that AMD was sort of influencing the system, the predominant species in the systems were something that was very tolerant: bullheads, white suckers. The really cool thing that happened in the 1970s was the Clean Water Act, and then there were a lot of remediation efforts where many of these small streams in West Virginia had limestone buffers put in to reduce that acid in the streams, and then subsequently leading into the Mon, ultimately increasing the fish community, and as I say here, it now actually supports a fairly diverse fish assemblage, and this includes some recreationally important fishes such as black bass, the sander species, and catfishes. In terms of the catfish population that we have in the Mon River, there's a lot of interest there. I'm going to get into that in just a second. Just as Rob Newman sort of pointed out yesterday, the effort, at least in terms of angling for catfish, regardless of what species you're talking about, has increased precipitously throughout North America, and this trend basically follows the same trend in West Virginia as well. And given this increased interest in the catfish population in the Monongahela River, West Virginia, we need to have some population assessments completed in order to make sure that we're managing this population correctly. And I think the one big thing that we're getting at here is that really prior to this point, and I'm not certainly not saying anything bad about Dave, because Dave is right there. Prior to this point of Kristen working on this study, there was very little known about the catfish population. And really knowing this, understanding this, can then provide insight to determine if actions are needed on that fishery. So that leads into the objectives of the talk today. The first is to assess the channel catfish population dynamics or demographics in the Monongahela River. And then we sought to simulate recreational harvest and determine if management actions are needed on the river. Would like to point out there's currently no minimum length limit on the Mon River, and exploitation rates are unknown. So those two things are very important for sort of where we go with this talk. So in terms of the field sampling methods, this is the Mon River. We sampled during 2018 and 2019. 4 pools were sampled throughout the Mon. There were 10 sites that we put hoop nets in. I'll talk about that in just a second. We had 40 sites in total. We used baited hoop nets with Zote soap, and this was actually pretty cool. First time that I'd ever played with Zote soap, and very, very little bycatch using Zote soap, so good for the turtles. A lot of field procedures that the field crews would carry out when they're out there capturing the catfish: date, time, temperature, what pool they're in, what gear was being used, what species were collected, total length, whether that fish was kept or released, etc. And then the laboratory procedures, these were very important for our modeling that we did with this study, but looking at length and weight, whether the fish were males or females or immature, and then of course otolith extraction, ovary extraction, egg counts, and ultimately fecundity estimates. So in terms of aging, just as we've heard several times throughout the symposium here, we mounted and processed the otoliths following Buckmeyer et al. 2002. We had 2 independent readers that aged these channel catfish. If consensus could not be obtained by both of those readers, the sample was discarded from the analysis. And the otoliths look really pretty. We also had to estimate fecundity, particularly for our spawning potential ratio models, and that's very informative because it provides that sort of critical threshold to determine where recruitment overfishing is occurring. And I'll talk a little bit more about that in a second. But ovaries were removed from the fish, weighed separately. We took a subsample of that ovary, subsequently counted the number of eggs in the subsample, and then extrapolated that back up to the entire ovary weight. This is actually a really nice ovary, and this is the majority of what Kristen got to count. But then we also had really ugly ones that look like this, where either the fish was reabsorbing the eggs, the preservation technique was not great, so we couldn't use some of these. And I guess the only reason that I put this in there is that everybody always puts their best foot forward, which we did there, but you also have to tell the truth that not all of them look like that. So for our fecundity estimates, we did some nonlinear regression there, and we were able to fit a line to this model. And then, like I said earlier, we're going to use this to evaluate whether or not recruitment overfishing is occurring, or at what exploitation level recruitment overfishing would occur. So just to jump right into the results here, over the course of this 2-year evaluation and lots of time in the field and time in the lab, 456 channel catfish were collected during this 2-year time period. Lengths ranged in size from 230 to 694 millimeters, so basically a 9-incher up to about 28 inches. 395 catfish were aged in this analysis, and what's sort of pretty cool about this is that we had ages ranging between 2 and 32, and if you think back to what I was talking about earlier with the Clean Water Act coming in the 70s, we're finally starting to see maybe some of the fruits of those labors with those older fish that are now showing up in the system, which is super cool. This is the length frequency distribution of the channel catfish that were sampled from the Mon River. The one really cool thing, and of course everybody in here has a length frequency distribution from their population, but this is actually pretty crazy that the mean size of fish that we collected was about 18 inches. 450 millimeter fish is the mean size. There's not a lot of those. There's not a lot of populations in the country outside of maybe the Red River of the North that have a channel catfish that are that big. Again, 395 channel catfish collected or were aged 2 to 32 years old, had a mean age of somewhere between 8 and 9 years. So when we take all of this data that we were able to collect, recruitment, growth, mortality, all of that information, we were able to plug it into the fisheries analysis and modeling simulator, and we modeled 3 different length limits given various exploitation rates to determine where these tipping points in the population would be. So one thing I'd like to point out before I go too much further with the modeling results is that just as you saw before, we had population ranging in age between 2 and 32, but really there's a lot of those that are outliers. It's not bad that we're seeing those, but in order to make sure that our model is performing on average, we took the average fish from our sample. So any of the age classes that we had fewer than 5 individuals, those were removed from the sample. And because of this, we ended up with the age structure between 3 and 18 for our simulation model. This is our von Bertalanffy growth equation, and this is ultimately one of the big parameters that we would put in the FAMS model. And you can see that given this really nice sample size that Kristen had, and clearly good age estimates, we had a pretty darn good fit that high R square that we see there. These are just the input parameters that are used for the FAMS model. One thing I'd like to point out here is that conditional natural mortality based on the Honig method was set at 0.21, and that's important to know because that's going to remain static with regard to all of the simulations that we did. We allowed our conditional fishing mortality to range between 0.05 and 0.95. We assumed that 100% of our females were spawning annually, and based on the dissections that we did in the lab, the percent of the population that was female was basically 1-to-1 male to female ratio. The last thing that I'd like to point out here on this slide for our input parameters is that we had basically 3 different length limits that we wanted to evaluate or assess. We had a 12-inch, 15-inch, and a 18-inch minimum, 300, 375, and 450 respectively. So this is actually the cool part of the talk where we actually get to see what these input parameters put into FAMS, what comes out, what does this mean for what's going on in the population. If you guys remember back to your basic fisheries management class, when you see these yield plots with yield on the Y, exploitation on the X, and I should point out this is the amount of yield per 1,000 recruits in the system. If you remember back to your introductory fisheries management class, you see that as there's a point in time where exploitation increases to a point, and then once yield begins to decline along that curve, at least with these yield plots, that implies that growth overfishing is occurring. And we see that here at about 35%. In the Mon River, at least under that 12-inch minimum length limit, that growth overfishing would occur in the population if harvest pressure or exploitation exceeded 35%. In terms of our spawning potential ratio models, this is, again, back to basic fisheries management class. When we do these spawning potential ratio models, we're looking at that tipping point where recruitment overfishing would occur. And so based on the Goodyear paper in 1993, he sets this threshold for resilient species at about, we have to maintain about 20% of the eggs in the system in order to ensure that recruitment overfishing doesn't occur. And basically what we see is that, I don't know why the line moved there a little bit, but it did, sorry. At basically a 12-inch minimum length limit, recruitment overfishing would begin to occur around 40% exploitation. So if you remember back, for growth overfishing to occur, we needed to have about more than 35%, and it makes sense. Growth overfishing starts to happen before recruitment overfishing would happen at 40%. And I think knowing those, or at least having an idea of where those tipping points are in terms of growth overfishing at 35%, recruitment overfishing at 40%, that's really important because we don't understand or know what these exploitation rates are for channel catfish within the Mon River. Kristen has here, and I think this is, I'm just going to say this verbatim, it's critical to prevent growth and recruitment overfishing from occurring to ensure the sustainability of this population, especially since these events occur so close to each other in terms of the exploitation level. So it's likely that if growth overfishing occurs, recruitment overfishing would occur before some management action could be taken on the population. And then at the end of the day, this would cause, big problems. So this is just a reiteration of basically what we would suggest, that the population at a 15-inch minimum length limit, you don't see any bending within that yield plot. And for the spawning potential ratio, that 15-inch minimum never gets below that 20% threshold. What we have suggested here is that the West Virginia Division of Natural Resources should impose a 15-inch minimum length limit for the channel catfish population in the Mon River. And despite not having any information on exploitation, we felt that this was a conservative approach, and given the increased interest that's on the channel catfish population. Really, I'm going to finish my talk by saying this, but a very special thanks to West Virginia DNR, also a special thanks to my former academic home, WVU, still go Mountaineers, and I would also like to thank my new institution, Missouri State University, for providing me the opportunity to be able to come to this meeting. And then I can't help but thank my lab and all the graduate students, undergraduate students within the Applied Fisheries Management Lab at Missouri State University. And with that, I'll take any questions if I have time.
We have time for a few questions.
Oh, come on.
No questions?
No, yes, thank you.
No problem. So I'm trying to remember back to the figure you had where you were saying that the growth and recruitment exploitation are close.
Yep.
But that's measured in yield, right? So what kind of numbers of fish would the difference be? As you drop down in size, you rapidly...
Yeah, that's a good point. I have no idea. Yeah, good point. I have no idea. Million? 500 million? 12? I don't know. All right.
I have a question.
Yeah.
Yeah, so you showed your fecundity relationship with lengthen.
Mm-hmm.
A little
Rough.
noisy, yeah.
Yeah, so...
Have you looked at it with age? Is it any better, or is it...
No, it's actually just, it's terrible across the board. And so what we did, one other part of this that I didn't mention here is that we actually went back in the literature and did some diving of other fecundity estimates and then put those into our model. And really, even though we had pretty crummy fit there, it really didn't change the overall picture of this 15-inch minimum. So basically the models perform similarly. So,
Any other questions?
thank you.
All right, thank you.